Welcome back, I'm that Chemist, and today we have 5 important papers in organic synthesis for the month of October 2022. The first paper is the perfluoroalcohol-mediated Diels-Alder reaction, reported by Diels-Alder's group. Some highlights of this paper include that perfluorinated alcohols promote Diels-Alder reactions, which is an extension of their prior work in this field, and the 2 main perfluoroalcohols that they use in this work are trifluoroethanol and hexafluoroisopropanol. These are used to mediate the Diels-Alder reaction as strong H-bond donors, and they demonstrate that perfluoroalcohols were superior to other alcohols as well as some aprotic solvents. In the case of these reactions, the perfluoroalcohol plays a role in hydrogen bonding to the diene or the dienophile without causing any decomposition of the dienophile. Typically, when fluorinated alcohols are employed, you want to do it to minimize reactions that could be caused by overly acidic solvents such as acetic acid. Alternatively, you might want to use this in the place of a Lewis acid, which might cause other side reactions, or Bronsted acid, which might cause side reactions, or might just be too acidic for your substrate. And perfluoroalcohols are appealing for this reason. They're really strong H-bond donors without being too acidic in most instances. So some fluorinated alcohols include trifluoroethanol, hexafluoroisopropanol, and perfluoroterbutanol, although this one's a gas. You can see that the pKa of methanol is 15.5, ethanol is 16.0, and then as we look at TFE and HFIP, they start getting a little bit more acidic, but these are still relatively low acidities compared to other acids, such as acetic acid, which has a pKa of 4.8. And so in this work, they examine a wide scope of different alcohols as well as non-alcohols as solvents. In this first scope, they examined Azadienes. Normally, these Diels-Alder reactions wouldn't work too well because the resulting product, enamine, would be too unstable. And the use of a bulky sulfonyl group also prevents side reactions where addition to the imine might occur. And as you can see here, they screened a number of solvents. And while aprotic solvents that were somewhat polar also worked, it worked much worse in the case of polar solvents like DMF and pyridine. Now, you might think that the improvement in yield doesn't justify the use of trifluoroethanol or hexafluoroisopropanol, but you'll see some cases later where the improvement is quite striking. I'm not going to go through the substrate scope for all of their work in this paper, but this is just to show here that several different azadienes were all well tolerated, and they could also change out the vinyl ether dienophile that they used, such as styrenes or this N-vinyl pyrrolidine here. They also compare the yields between trifluoroethanol and dichloromethane, and you can see dichloromethane is worse in every instance. Now, the next class of heterodiene that they look at is 1,2,4,5 tetrazines. And when you do Diels-Alder reactions with tetrazines, you form nitrogen as a byproduct. And in this case, because they're using norbornadiene as their dienophile, this forms cyclopenadiene as a byproduct. So this is likely why they needed so many equivalents for this reaction, so that the norbornadiene is able to react with their cyclopenadiene byproduct, which is another diene that can react with this really reactive dienophile. Here you can see a difference in kinetics between chloroform and hexafluoroisopropanol. You can see a significant rate enhancement when the fluorinated alcohol was used. And they have a scope of different alkenes and alkynes that were used for this reaction. And one that I thought I would include because it was kind of neat was the use of indole. Normally you don't see indole in Diels-Alder reactions, so this is kind of a neat example. Additionally, in some of their prior work, they've examined the effect of fluorinated versus non-fluorinated alcohols for the hetero-Diels-Alder reaction of tetrazines with these 2 methyl thio groups. And when hexafluoroisopropanol is used, you end up getting a triazine product, although when methanol is used, you end up getting this 1,2-diazine. The outcome of Diels-Alder reactions could be greatly affected by whether or not fluorinated alcohol is used, especially in the case of these tetrazines, as they demonstrate. In addition to the tetrazines, they examine a wide range of different triazines. Here you can see if, for instance, norbornadiene was used, they get substituted pyridines as their products, which I thought were kind of cool. Additionally, if they use this enamine with a 1,2,3 triazine, which I wasn't even familiar with as a class of reagents prior to seeing this paper, in this case, they also get pyridine derivatives. In all instances in their paper, fluorinated alcohols provide improved yields compared to non-fluorinated alcohols. And one other example here is where they take this 1,2,3 triazine and using different ketones and aldehydes, they're able to make substituted pyrimidines. And I thought that this was really neat because they're just using enols essentially, which will eliminate afterwards to form the corresponding double bond. Definitely a neat strategy, and I'd encourage you to check out the scope in their paper. Definitely really cool to see. but not as cool as my segue to our sponsor. Today's video is sponsored by Reaxys. Reaxys is my preferred chemistry information system for searching chemical reactions and related literature. They also have a free app for iOS and Android called Reaction Flash. Reaction Flash is an app with over 1,000 named reactions in organic chemistry, and you can quiz yourself on how these reactions work, what reactants are used, and what sorts of products are formed. I have specifically used Reaction Flash as a way to learn more reactions that may help me come up with new ideas for my own research. The app allows you to view the mechanism of named reactions, test your knowledge with an interactive quiz, and search through numerous specific examples of these reactions from peer-reviewed literature. Thousands of students and researchers already use Reaction Flash. Reaction Flash is a great app as an up-to-date reference and learning tool for chemical reactions, so why not download it today and give it a try? You can download it on iOS or Android by clicking the link in the description. That way they'll know that you came from this channel. I want to thank Reaxys for their support of this channel. The second paper for today is the synthesis of Pleuromutilin antibiotics by Seth Harrison's group. I really like this paper because it was quite elegant. Some highlights of this paper include a Vinylogous Wolff-Rearrangement as a key step for the synthesis of their analogs. They produce a platform for the C12 modification of Pleuromutilin analogs, and they examined a small combinatorial library of ester derivatives of their C12 functionalized Pleuromutilin analogs for antibacterial activity against gram-positive and gram-negative bacteria. The development of new antibiotics is an area of interest, and this paper is pretty awesome for that reason. Here you can see the structure of Pleuromutilin. The C12 position is well tolerated for making substitutions, and R1 can be various different thioether derivatives, and those are the two key points of functionalization that they're interested in looking at, although some other functionalization of the core has been demonstrated in their paper as well. So in this paper, the key step is this Vinylogous Wolff-Rearrangement reaction. In their prior work making Pleuromutilin as well as 12C-epi-Pleuromutilin, they had developed this cyanation strategy, although it didn't generalize. So in this work, they do some cyanation chemistry as well, but before that's necessary, they came across this Vinylogous Wolff-Rearrangement. So your typical Wolff-Rearrangement is where you have a diazoketone. In this case, they use the Azadienes reaction. And what this does is this just converts an acyl chloride to an alpha diazoketone. So here what they do is they start with the methyl ester, they hydrolyze it to the corresponding acid. This is converted to the acyl chloride using oxalyl chloride, and then it's treated with diazomethane via the Azadienes reaction. So once this happens, they treat it with silver acetate in the presence of methanol, and your typical Wolff-Rearrangement would result in a 1-carbon homologation. So they start with a carboxylic acid, and they end up getting a carboxylic acid which has gained 1 CH2 in between. Now, because they use methanol instead of water, they get the methyl ester. Now, in addition to the product that you'd expect, they also get this different product, product 13. And because of this rearrangement, they're able to change their strategy a little bit. So this Vinylogous rearrangement could go through a concerted mechanism as shown above. I personally believe the concerted mechanism for these types of rearrangements to be more likely unless they're done under photochemical conditions. Here, this carbene-mediated mechanism is also possible, but I think the top route is more likely. So once they make this ketene after the rearrangement and the elimination of nitrogen, it reacts with methanol to protonate this alpha position, and then they get ester 13. Now, once they have ester 13, they have several common intermediates. So initially, they have their cyanation reaction, which I thought was kind of cool. It's a 1,4 addition of cyanide to a Michael acceptor. This is done in a diastereoselective fashion with 20-to-1 selectivity. The next step is to form this ketal, and so they do that using TMS triflate as a Lewis acid. Carbon 10 is lithiated and methylated using LDA and iodomethane. And this nitrile and the ester are both subsequently reduced using dibol, followed by workup with acetic acid, giving an aldehyde at carbon 14, while they also get a primary alcohol at carbon 11. Now, this titanosine-mediated propargylation reaction is something comparable to a Grignard reaction. They had pulled this reaction out of the literature, and they were able to get the desired diastereoselectivity really well. You can see 37-to-1 diastereoselectivity, and this is one of the important branching points in their synthesis. So they can do this reaction with different propargyl bromides if they want to get functionalization at what ultimately becomes carbon 12. Once this has been added, they undergo an IBX oxidation to form an aldehyde at carbon 11. Carbon 11 is then able to engage in this reductive cyclization reaction, forming this allylic alcohol in product 23. This carboxylic acid 22 is then activated using a mixed anhydride with benzoic anhydride. and that's then able to esterify this alcohol. Once this ester derivative's been made, they're able to reduce this double bond, and with different analogs of this final product here, they get various different ratios of diastereomers at position 12. I think that this has to do with their choice of ester, but it might also be influenced by the group coming off of carbon 12. So 24 is the product that they get using just typical propargyl bromide and without exchanging this ester group. The other point that they can vary the synthesis is by changing the ester group. And so this can also be exchanged with different analogs. So those are the two key points that they want to functionalize their compounds in this paper. They have a decent scope of analogs that they explore. Here you can see different propargyl groups have just been used. And once this has been done, they're able to do that reductive cyclization, and they're able to put on different ester groups. If you want to know how they do that, I'd encourage you to take a look at their paper. Here is an antibacterial screen of some of the Pleuromutilin analogs that they prepared. Here are 4 of their best performing compounds. You can see the diversification at carbon 12 is somewhat minimal in these cases, although the R group on the sulfur tends to change. However, there is still really good activity for compounds 63, 67, and 68, although 63 to 68 all have long chains at carbon 12. So it isn't just this SR group that can be varied and still have activity. You can see if we look at 63, for instance, there's still decently high activity. A small number means that there's effective inhibition of these bacteria. If you need additional cases, here's 67, here's 68, and then there's other analogs that they examined that I didn't have room for in this slide. So this is a really cool paper. It's definitely exciting to see new antibiotics being developed, and I wonder if we'll be prescribed any of these analogs anytime soon. The third paper for today is the use of 2 Ladderanes as Isosteres. This is from Thomas Fassard and Kevin Brown's groups. And what they do in this paper is they produce a new isostere for a meta-substituted arene or a more rigid isostere for 1,3-cyclohexane derivatives. So they show here that the distance between this red group and this blue group is 5.1 angstroms. This is what you'd have for your typical meta-disubstituted arene. There are other motifs that have been developed recently which are similar isosteres. So you can see these bond distances are quite similar, although the angles change to a certain extent. And in this work, they make these 2 Ladderanes, which are pretty close in terms of bond length, both between the green and the purple dot, as well as the blue and the red dot. You can also imagine that this is just a cyclohexane bridged through the middle 2 carbons. So this is technically still a cyclohexane, albeit a very strained one. So in this work, they develop rigid isosteres to mimic the metasubstitution of aromatic rings, and they prepare a suite of novel 2 Ladderanes on a gram scale. Not only do they produce these cis-substituted 2 Ladderanes, they also produce a number of trans Ladderanes, as the trans isomers are produced on the way to making the cis isomers. So the way that they do this is first they do a Grignard reaction with this homoallylic Grignard reagent. After this has been done, in a flow setup, they're able to undergo a photochemical 2+2 cycloaddition reaction. This forms this 4,5 fused bicyclic system. The stereochemistry of this alcohol is inconsequential because it gets oxidized by DMP to the corresponding ketone, which is then able to be diazotized in the alpha position using this diazotransfer reagent. The next step is to generate a carbene photochemically, so this is done in flow. This allows for a Wolff-Rearrangement to occur. And once that ketene is formed, it's trapped by methanol, affording this trans 2 Ladderane product. Now, if the R group is a phenyl group, to get the cis product, first they have to cleave the methyl ester and epimerize this alpha position. So when this is treated with water and terbutoxide, it hydrolyzes the ester as well as epimerizing that center. So they need to remethylate it, and so they do that with iodomethane and potassium carbonate. And then they do an oxidative cleavage of the ring using ruthenium chloride and sodium periodate. Alternatively, if they have this alkene group here, they're able to do an ozonolysis reaction to afford the aldehyde and reduce it with sodium borohydride to get the alcohol. They can then protect that alcohol with TIPS chloride and then undergo epimerization of this position to afford the corresponding carboxylic acid. So they make various different analogs in this paper. I'm just summarizing a few of the different ones here. Here you can see some other analogs they make. In this case, they don't epimerize, they just do the oxidative cleavage of the arene to get this trans isomer. This can then be activated through a mixed anhydride to form this amide derivative, which can then be reduced with LAH to get the amine. Alternatively, lithium borohydride can be used, and this will just reduce this ester group to a primary alcohol. And depending on the conditions that they choose, they'll get different products. In this case, you can see lithiation of this position allows for the functionalization with carbon derivatives such as al bromide. Some other analogs that they made are shown here, but I wasn't able to include all of this in this presentation, so I'd encourage you to go check out their paper. The fourth paper for today is the total synthesis of Psammaplysin A. This was reported by Thomas Maguire's group. Some highlights of this paper include the 13-step racemic synthesis of Psammaplysin A. They also do several manipulations of a complex sensitive scaffold. I think looking at this target, you can appreciate why it's so interesting. This was definitely an eye-catcher when I first came across it. So in this paper, they explore several different synthetic routes. For the sake of brevity, I think we're just going to talk about the main one predominantly. Initially, they do this alpha bromination of this 1,3-dicarbonyl species. This is drawn as the enol just for simplicity. Once this alpha bromo species has been prepared, they do a Henry reaction with ethyl nitroacetate. This is essentially a nitroaldol reaction. This gives a mixture of diastereomers at carbon 7. The polar one ends up getting stuck in silica. The nonpolar one is the desired product, which they confirm by X-ray crystallography. And the nitro group is able to displace that bromide, forming this spirocyclic system. Now, the main strategy that they ended up using for their paper was the reduction of this NO species to afford spirocyclic isoxazoline 18 using triethyl phosphite. They then attempted doing a Baeyer-Villiger oxidation to install this lactone group, although when they tried to TBS protect this alcohol, they ended up getting this weird reaction where they formed this ethyl carbonate group. And the identity of this is a little bit weird. You can see this is in 46% conversion. And so what happens is one molecule of this starting material reacts and forms ethyl cyanoformate. And the cyano group of ethyl cyanoformate is likely a good leaving group. And so this is able to form a carbonate derivative on the other 50% of the unreacted starting material. So kind of an odd side reaction. I thought I would remark on it because it's kind of a neat one. So instead, the different route that they had to take was the treatment of this alcohol with TBS chloride before the Baeyer-Villiger. Then they do the Baeyer-Villiger, that works fine. Then they want to get rid of the carbonyl group, but they want to have a double bond there. So they treat this with potassium HMDS in the presence of this phosphonyl chloride, forming this vinyl phosphonate product. This vinyl phosphonate is then able to be reduced with palladium and a silane reductant, affording this vinyl ether 25. This is the key building block that they needed moving forward. So once they have compound 25, they screen several different oxidants in the presence of different transition metal catalysts, and they get this lactone as well as this vinylogous lactone 26. So lactone 27 wasn't the desired product. They wanted vinylogous lactone 26. So what they ended up doing is just hydrogenated that double bond, and then they could push material forward to continue the synthesis. So they were still able to use this, then treat it with that phosphorylating agent and reduce it back to compound 25. So vinylogous lactone 26 then underwent bromination in this alpha position to give this vinyl bromide, followed by a subsequent bromination using this tetrabutyl ammonium tribromide salt in the presence of ditert-butyl peroxide, giving product 28. They found that the yield was higher when they telescoped this over several steps without purifying, and they then need to form this double bond and a methyl ether. So they use potassium HMDS and methyl triflate, and the potassium enolates methylated effectively. And one of the last steps they needed to do was the hydrolysis of this ester to get the carboxylic acid, but it was too unstable when they tried to isolate it. So what they needed to do was use these weird conditions with TMS-OK. This was hydrolyzed in situ. They then used some rather unique coupling reagents in the presence of amine 29. This then gives them the desired amide 30. They then deprotect this TBS group and deprotect the phthalimide group of this nitrogen with hydrazine, producing the desired product Psammaplysin A. So I thought this was an impressive synthesis and definitely a cool one to see. Now, the last paper for today is in honor of Dave Evans. Dave Evans passed away earlier this year. And when he was still with us, I found out that he had a Twitter, and I was amused by his Twitter handle. So hopefully at least a couple of you are amused by that. He still has links to a lot of his physical organic notes on his Twitter. If you haven't checked those out before and you're interested in organic chemistry from a phys chem perspective, it's definitely worth checking those out before they might get lost to the sands of time forever. Additionally, this paper is from Jason Biger's group. So this is a really long total synthesis. It was an enormous synthetic achievement. Just looking at this molecule here, you'll probably be blown away by the total synthesis of Aflastatin A. The synthetic sequence for this compound is much too large to have in this video, so I'd encourage you to go check out the paper if you're interested in looking at aldol chemistry. There's a lot of really hardcore aldol chemistry, and if you like aldol reactions, all different sorts, this is the paper for you. It's enormous. So just briefly here, we have the retrosynthetic pathway. You can see it's a fairly convergent synthesis, which is nice to see. Convergent syntheses are nice because then you can make decent amounts of your intermediates and couple them all together right at the end, rather than getting smaller and smaller and smaller and smaller amounts through a typical linear sequence. Now, I would hate to be the one looking at NMRs of this compound at all, at any stage, but hey, they managed to prepare the compound, and this is a massive synthetic achievement. So I'd like to congratulate the authors for all their hard work towards this project. This month, we have even more honorable mentions. This list may look extensive, but there was probably at least another 10 that could have gone on here in terms of being really useful organic papers that are worth your time to check out. These are all really good papers, and if you have a couple minutes to spare and look at each one, I'd encourage you to do so, because there's some pretty cool ones in here. I'm going to give one shout out to this sulfur chemistry one, because I thought this was kind of cool. It's got a CC bond cleaving reaction from tetrahydrothiophenyl derivatives. So a really cool paper, and I'd encourage you to check it out. So hopefully you've enjoyed this month's episode of Important Papers. If you haven't seen this series before, I release one video per month. And if you haven't used Reaction Flash, I'd encourage you to download the app. It's free. And by using the links in the description, they'll know that I sent you. Thanks for watching, and I hope you have a great day.